In this example, I'm going to do Coletta 919, which is talking about a fisherman. And what happens is he's fishing, a fish strikes the bait and pulls on the line, and we know the tension that the fish pulls with. We want to know how many revolutions of the reel occur in 1 second if the reel has a moment of inertia that we know, and we also know the distance of the line from the reel's axis, and we can assume that it's a negligible friction. Wow, this one's hard for me to picture, so I'm definitely going to have to start with some analysis and see if I can figure out what kind of problem this is. So see if you can pause here and do the analysis and planning for this problem. All right, here's my analysis. I don't know too much about fishing, so I just drew a really rough sketch here where here's the reel, and that's where the fishing line is wound around, and then it's connected to the fish. So if the fish is pulling here with 65 newtons, that ends up pulling on the reel with 65 newtons, because remember, ropes only have one tension. And there's kind of like a pulley of some kind here at the top of the pole. Yeah, like I said, not a fishing expert, but I do know enough then to take a free body diagram of the reel here, which is what I care about. Since we're neglecting friction, there's really only one force on the reel, and it's out here, a tension force of 65 newtons, and it's tangential, so it's actually at a 90-degree angle to the radius, which we know the radius, and we also know the moment of inertia, that's I. So here's that free body diagram. And just looking at this, I'm already thinking, I know enough to find torque because I have a force and I have a distance from the axis of rotation. Ooh, I should have drawn the axis of rotation in here. That's this right there in the center. That's the axis of rotation. All right. So if I wanted to, I could figure out the torque, and I have I. So that could be a rotational dynamics question. Then I also realized that maybe it could look a little bit like a kinematics problem, because I know a start and end, like right before the fish pulls on it, it hasn't moved at all, right? It hasn't gone anywhere. Theta naught 0. It's not rotating at all, so its angular velocity omega naught is 0. Then at the end, 1 second later, right, because what we care about is how many revolutions of the reel occur in 1 second. 1 second later, we don't know how fast it's going. We don't know how, through what angle it's rotated, but we do know that it happens 1 second later, right? And so then the goal is that we want the number of revolutions of the wheel, which is theta, right? So this is critical, identifying that our goal is theta, right? So this is sort of like if we knew that somebody had started at rest and we knew the forces on them and we wanted to know how far they had gone, right? Theta is like a displacement. So sometimes it helps to think of this like a linear analog. So see if you can either use that technique or use the analysis I've done so far to make a plan for this problem. Go ahead and pause and make your plan. All right, here's my plan. But before I go into the details of the plan, let's think about how I got there. All right, so my goal is theta, and really kinematics seems like the best way to find theta, the distance that the reel has rotated through. But I can't just use kinematics the way it is because I have 3 missing variables, right? And remember, to use kinematics, I only better have 2. And so I can't think of a good way to get this. This is our goal, but what we do have is we have a great way to find the angular acceleration, right? So this is sort of a classic rotational dynamics problem, right? We know about forces and torques, which we can then use to figure out the angular acceleration using the sum of the torques equals I alpha. Then once we have alpha, we can go back to the kinematics. We can fill alpha in here. Then we'll only have 2 unknowns, and we can do kinematics. This is a lot like a linear dynamics problem where, say, we knew the forces on the object. We'd use the forces to find the linear acceleration of the object. And then once we knew the acceleration, we could then do the kinematics to see how far the car had gone or something like that. All right, so go ahead and pause here and see if you can execute this plan. Here's the start of my execution, right? Sum of the torques equals I alpha. So the first thing I need to do is figure out the sum of the torques, right? Because eventually I'm going to use this alpha equals the sum of the torques over I, right? Just an algebraic rearrangement. Well, the net torque, which is all the torques together, is just the torque from F because there's no other forces acting on the reel. And then remember, to get torques, we just do F times R times sine theta, where F is the magnitude of the force, R is the distance from the axis of rotation, and sine theta is the angle between those 2 lines. And here, a string pulls at 90 degrees around a pulley. So here, that theta would be 90 degrees, which gives us a 1 from sine theta. So if I plug those in, I just get 2.6 Newton meters. So that's the torque. And then once I know the torque, I can plug in here to get alpha. I get 650, and I'm careful with my units, right? So torque is Newton meters, which is kilogram meters per second squared times meters. And then moment of inertia is kilograms times meters squared. So we have the kilograms canceling. The meters squared cancels with this meter, and we're just left with 1 over second squared. Right, sorry, 1 over seconds. Yeah, squared. 1 over second squared. But then if we think about what alpha is, it's an angular acceleration, so it should actually be radians per second squared. And remember, radians just sort of a placeholder, so the fact that you don't see it here shouldn't bother you. It doesn't really have any units, and you can just throw it in to make the units right, like this. So we have an alpha of 650 radians per second squared. So we've done this part. We've used the torque to get alpha. So this is a rotational dynamics. And then now that we've done our rotational dynamics, we can switch into doing our rotational angular kinematics. So I can fill alpha in down here and continue going. Go ahead and see if you can do that second part of the execution. All right, when I looked at my knowns and my goal, I realized this was the right equation to connect the two of them. Theta equals theta naught plus omega naught t plus a half alpha t squared. And it's really handy when solving this because we know that we start with 0 angle, we start with 0 angular velocity, and so it's just theta equals a half alpha t squared. I can plug those in and I get 325 radians. Nicely, the units worked out, and that's the angle that I've rotated through. But if we look at our goal, it's the number of revolutions of the wheel. So it's actually theta, not in radians, but in revolutions, right? In revolutions. So now we want to do a unit conversion from radians to revolutions. See if you can remember what that unit conversion is and do it now. All right, that conversion is 1 revolution is once around a circle, which is 2 pi radians. So that ends up giving us 52 revolutions if we are careful about our significant figures, which should be 2 significant figures. Almost everything here has 2 significant figures. Now, at the end, you want to do some monitoring, and one of the things you might want to put in your monitoring, well, first of all, 52 revolutions seems relatively reasonable. It's been 52 times in 1 second. You know, when you catch a fish, that reel moves pretty fast because it's small. But another thing we might want to typically check in our monitoring is sines, right? And one of the things when I calculated my torque is I forgot to do the step where I check the sine of the torque, right? This torque would, the way I drew it, would be making the reel spin clockwise, which actually means that I'm missing a negative sign, right? And it's just something I have to throw in right up here when I'm calculating the torque, because one of the steps of my torque problem solving strategies is to just check the sign, right? So then this would be a negative sign right here for my alpha. Let me just throw in a couple more negatives, right? There's one there. Then when I plug it in here, this would be negative, negative, negative. Let me just highlight these with the arrow. So I put a negative here, and then here, this alpha turns out to be negative now, right? So it turns out that I went counterclockwise, which means that I went negative 51.7 revolutions. But we just really care about how many revolutions of the reel occurred, and it doesn't even ask about which direction they are. So we don't really care clockwise or counterclockwise. So it's still right to just put a 52 revolutions here. If you put a negative 52 revolutions here, that would also be right. All right, I think we finished this problem.